Hello, my name is Yile Wang, supervised by Professor Ke Yi from the Hong Kong University of Science and Technology. I'm very pleased to introduce our paper, Secure Yannakakis, to all of you. What does secure Yannakakis mean? It is actually a cross-field work between security and database. For secure, we refer to the secure multi-party computation model, or the so-called SMC model. In this model, there are n parties. Each party holds a private input xi, and they want to jointly compute a public function f while keeping their inputs private. SMC model has wide applications nowadays. For example, it can be used in secure auctions, anonymous voting, or federated learning, which is a very hot topic recently. Of course, it can also be used in query execution. For Yannakakis, we refer to the generalized Yannakakis algorithm that can compute some queries in time input side plus output side. This complexity is instance optimal because at least we require order in time to read the input, and we require order out time to print the output. Therefore, this algorithm is very efficient and practical. What if secure meets Yannakakis? We may ask, can we also compute these queries efficiently and practically under SMC model? Secure Yannakakis says that the answer is yes. Our model is defined as follows. We consider the case when there are exactly two parties, Alice and Bob, and they want to jointly compute a public, a cyclic, and a free connect join aggregate query. Each relation in the query is fully held by either Alice or Bob. After computation, Alice will learn the query result, but not any more information. Bob will learn nothing. Compared with previous work, SMSQL, we have successfully reduced the running time from exponential to almost linear, which is only worse than the non-private model algorithm by a log factor. Therefore, this algorithm is also very efficient and practical. Why do we choose secure Yannakakis? Beyond theoretical analysis, our experiments demonstrate the improvement better. The running time of secure Yannakakis is very close to the query time of MySQL in non-private model, which is much faster than SMSQL. For example, on the 5 megabytes dataset, SMSQL requires more than 300 years to compute TBC-H query 3, while secure Yannakakis only requires 20 seconds. It has brought joint aggregate query execution from only theoretical to practical. Here we use a simplified example to demonstrate the usage of secure Yannakakis. Suppose an insurance company has two tables, R1 and R3. R1 contains the information of co-insurances of all the users, while R3 includes the classification of diseases. On the other hand, the hospital has a table R2, which includes the information of the patient. Now, suppose the insurance company wants to estimate the amount of payment classified by disease types, which can be expressed by this query. In non-private model, of course, the hospital can simply send its table R2 to the insurance company, and the company can then compute the query in time in plus out by generalized Yannakakis algorithm. However, under SMC model, this is not allowed because we need to ensure the privacy of R2. Using secure Yannakakis, after computation, the insurance company will learn the query result, but not the hospital's data. the hospital will not learn anything about the insurance company's data. Now we talk about which query can be computed by secure Yannakakis. First, let me introduce some background in database theory. Join, or natural join, is the most interesting operator in relational algebra. The join of two relations are the tuples with the same values on the common attributes. For example, the common attribute of AB and BC is B. So for each tuple from AB and each tuple from BC, if their value on B is equal, then they contribute one tuple to the query result. We can use a join tree to join multiple relations. The join tree is a tree such that each node corresponds to a relation in the join query. And for each attribute, the nodes that contain the attribute form a connected component. If there exists a join tree, then the join is called a cyclic join. For example, consider the query AB, join AC, join BD, join DFG, join BE. Then this is the valid join tree for this query. For each node, it corresponds to a relation in the query, and for each attribute, for example, let's look at attribute B. The relations that contain attribute B are R1, R3, R5, and they're connected in the join tree. Since the query has a join tree, the query is called a cyclic join. An acyclic join may have different join trees. For example, this is also a valid join tree for this query. The standard Yannakakis algorithm can compute any acyclic join in time in plus out. Given the join tree, standard Yannakakis first do semi-joins to remove all the dangling tuples of the relations, and then compute the join in arbitrary order. The semi-joins are performed in the bottom-up manner and then the top-down manner. Still, let's use this example to explain the semi-join phase. In the bottom-up phase, the relation R3 semi-joins its children R4 and R5, and then R1 semi-joins its children R2 and R3. Afterwards, in the top-down phase, the relations R2, R3, R4, R5 semi-joins their parent in the given order. That's all about semi-join. Now let's turn to join aggregate query, which is a query having joins, selections, and aggregations. A join aggregate query can be expressed by SQL in the form select attributes, aggregations, from joins, where conditions grouped by attributes. We have two restrictions here. Each aggregation is applied on attributes of a single relation. Each filter is applied on attributes of a single relation, and the filters are connected by AND operations. For example, the query 3 in TBCH is a very standard join aggregate query. Not all join aggregate queries can be computed easily, so we introduce free connects. A free connects join tree is a join tree such that the output attributes are higher than non-output attributes. For example, let's look at this query select BDEF, sum D plus F times G, from R1, join R2, join R3, join R4, join R5, grouped by BDEF. The output attributes are BDEF, which are underlined, and the non-output attributes are A, C, and G. In this join tree, top A is R1, top D is R3. Since top A is higher than top D, this is not a free connect join tree. At the same time, this is a frequency join tree, which can be easily verified. We call an acyclic aggregate query frequency if it has at least one frequency join tree. Therefore, this query is frequency because of this frequency join tree. The generalized Yannakakis algorithm can compute any frequency join aggregate query in time in plus out. Here, we use this join tree as an example to illustrate the idea of the algorithm. It works in a bottom-up manner. First, let's look at the leaf, R2AC. C is an attribute that is not related to its parent, R1. So we remove C by a projection on A, which is step 1. Afterwards, R2 has only one attribute A, which is a subset of the attributes of R1. Therefore, we compute R1 join R2, which is essentially a semi-join, and then R2 can be removed. Next, we go to the leaf R1AB. A is an attribute that is not related to its parent, so we remove A by a projection on B, which is step 3. Afterwards, R1 has only one attribute B, which is a subset of the attributes of R3. So we compute R3 join R1, and then remove R1. Similarly as before, we remove the redundant attribute G by a projection on DF, which is step 5. Finally, all the attributes are output attributes. Therefore, we compute the final result by computing the full join R5BE join R3BD join R4DF. Note that all the semi-joins or projections can be computed in order in time, and the full join can be computed in plus out time by standard Yannakakis. Therefore, the total running time of generalized Yannakakis algorithm is also in plus out, which is instance optimal. How to achieve the same complexity on the SMC model? The high-level idea is actually very simple. We just build a protocol for each relational operator and connect them together. Recall that the generalized Yannakakis algorithm has 3 types of operators: projection or aggregation, semi-joins, and joins. For projection or aggregation, let's look at this example, sum B grouped by A. We first sort the relation R by A such that all the tuples with the same values on A are consecutive. Then we use a linear garbage circuit to compute the sum of each pair of neighbors. For example, if A1 is equal to A2, then we add B1 to B2, and B2 prime is equal to B1 plus P2. Otherwise, A1 is not equal to A2, then B2 prime is still B2. For semi-join, to avoid quadratic complexity, we use the standard private set intersection protocol, which runs in linear time. For join, we observe that tuples in the join result will reveal all non-dangling tuples in the original relations. Therefore, we can simply reveal these non-dangling tuples to Alice, and she can compute the join result in non-private model. This is safe because anyway, Alice should take the final join result, which has already included this information. Here is the conclusion of our paper. We proposed secure Yannakakis, a protocol that computes frequency join aggregate query on the SMC model. Our theoretical analysis shows that secure Yannakakis is very efficient. Our experiments shows that secure Yannakakis is very practical. We plan to do the following things in the future. We want to support different SMC models and more types of queries. We want to build a system that analyzes SQL and generates secure Yannakakis code, which has almost been done. We also want to integrate with differential privacy, which is also a very hot topic recently that can protect privacy. That's all. Thanks for listening.